Good morning, ladies and gentlemen. Here am I. We go on with our course of quantum transport, and you're already pretty used to this fact. There is yet another change of topic. Although there is some link. Last time, we've been talking about quantum corrections to classical transport, which is a manifestation of interference. Now we are going to kind of ultimate interference. Localization will be talking about localized states in quantum dots. Right, we will define quantum dots first. Then we will talk about discrete levels, look at simple models, electrons in a box, electrons in a ring. We will talk a little bit about interesting topic of persistent current, magnetization current in the dots. Right. Having understood levels, we will assess the states, quantum mechanical states, which are made by different occupations of these levels. Right, and with this we could talk about transport in quantum dots. There will be also homework about this, and there is a chance that it will come in course of examination. Right, so we will be talking about the Coulomb blockade, which is also manifested at quantum dots, and we will talk a bit about this. Next to it, I would like to tell you more about the levels in quantum dots that will allow us to assess interesting topic of chaos and order in particle motion, in electron motion in particular. We will understand that most dots are in fact chaotic. And the spectrum, in this case, is described by means of random matrix theory. An example of random matrix theory we have seen a week ago. Now it will be also random matrix technique applied to quantum dots. So there is a program for today. Let us go for this. Right. First of all, I would like somehow to define what is a quantum dot. Parts of this definition are kind of obvious. In any case, we are talking about electrons, which are, in a good approximation, disconnected from all other electrons, forming a place. They're confined in some place. And by general laws of quantum mechanics, if the motion is quantized, is confined, it is quantized, and all these electrons must be in a system of discrete levels. Yeah, but one should not exaggerate, one should not remain practical. If we, for instance, take Eiffel Tower and isolate it from the ground, then formally it will be a quantum dot. But, well, the volume of the tower is such that the distance between neighbor levels is completely invisible and inaccessible. So we talk about quantum dot only if our experiments show that this is a dot. It's not something else. Uh, we talk about quantum dots only if the discrete levels in these dots are visible. Fine. This further step, we can classify the dots, and basically there are two classes. The dots where design does not imply any leads, disconnected dots. And in this case, well, how to assess them? It is possible. You just shine light on this dot, or you look at the reaction, and thereby you can assess the levels, everything experimentally. An alternative is to connect some leads. Of course, we need to make sure that the connections are not, that the contacts to the dot are not too transparent, otherwise the state will be delocalized. And in this case, we also encounter once again our central topic of this course. We encounter conductance quantum. A conductance of the contact, in order for levels to remain discrete, must be smaller than, the conductance of the contacts must be smaller than conductance quantum. Good. What is about visibility? Right. For well visible levels, we need the distance to be, well, something about 1/10 of milli-electron volts. Well, although voltages can be corresponding to the level energies can be measured with high precision, it is somehow difficult to measure it in the context of nanostructures. So 0.1 remains for several decennia already good estimation, good number. If we talk about metal islands, just made from metal, for instance, mercury or aluminum, with dimensions at nanoscale, like 100 nanometers, we have, 100 nanometers. We have estimated already level spacing in lecture number 5. We have found 10 to the minus 8 electron volts. That's why at the modern level of technology, we cannot see quantum dots in artificially made metallic structures. But well, we can do it from, for instance, semiconductors, when the wavelength is much bigger. Good. I guess we need to have some orientation. So here, there are some pictures of quantum dots. Let me call it picture A, and let me call it picture B. And right, it's again training for multiple choice questions. So which dots are disconnected? A or B? Please put your questions to the chat. More opinions? Okay, it didn't work to cheat you. Fine, yes, B is a correct answer. First of all, right, obviously there are no obvious connections to in figure B and in figure A. And yeah, so one could think of both. But in fact, yeah, if you look at figure A, first question, where are the dots? Who can tell me, well, it's already not a multiple choice question, but who can tell me where are the dots in figure A? Try to make it descriptive. Okay, so the dots, they are on the dark brownish part in between the lighter gates. Yeah, okay, good, right. I believe you have seen it somewhere. If I were given this question, I would never answer. But you're right. The dots are, there are two dots here and here, or at least they want to do this. The point is that the whole structure is a two-dimensional electron gas, and they put, like in the experiment we have considered in the first lecture, the system of gates on the top of it, depleting electron gas underneath. Right, so they make dots, and they also make a system of leads. Right, so now I will make red electron gas which is not depleted. Here and here it's not important. So they arrange somehow the transport in this way through both dots. Good, so it's quantum transport. To confuse a bit, sometimes people talk about quantum dot, about something like which reminds the dot visually. For instance, chaotic cavity, which we have looked at once, also could visually could remind the dot with some barriers. And but in this case, for chaotic cavity, since there are open external leads, well, it's high transparency, so conductance must be in any case bigger than conductance quantum, and there are no discrete levels in such dot-like structures. So for me, they are not qualified as quantum dots. Fine, okay, we've got general definition. Let us consider perhaps a concrete example. Right. I want to get discrete levels in a simple situation. So I simplify it as much as I can. So let me take again two-dimensional electron gas, and let me put the gates. Okay, let me put gates explicitly to form a square quantum dot. Right, and I will assume that the potential of the gates, eventually it's pretty experimentally relevant. The potential of the gates is very big, and what we have here is a box potential. So the potential is infinite at these boundaries, and I wonder what are electron states. All right, we perhaps can recall that we talk about waveguides. In this case, the motion is quantized in both directions. What does it mean? It means that, let me get a bigger size of the dot. For instance, there is a wave going in X direction. It is reflected and it becomes a wave in opposite direction. And these waves interfere to form a standing wave with nodes at the boundaries. Okay, there is a situation with no nodes, there is a situation with, with two nodes at the boundary. There is a situation with three nodes, four nodes, and so on. That gives us all possible standing waves, quantization of corresponding wave vectors. Both wave vectors are quantized in X direction and in Y direction. So what I did here, I replaced these K vectors in kinetic energy of the dot by discrete numbers. Fine, I got discrete levels. Now I would like to understand the average space in between these two levels. And for two dimensions, okay, it's pretty easy to derive that in average, the spacing does not depend on energy, but inversely, as we expected, inversely proportional to the area of the dot. Good. That constant which I gave it for gallium arsenide heterostructures for gallium arsenide quantum. So from this one can assess that dots are visible if the size A is, levels in the dots are visible if they are about 0.1 micro electron volt if the size of the dot is somehow like 100 nanometers. Fine. What else would I have to say? Well, about the levels, right? As we see, levels form a rather regular series. So within each series, I fix n squared y and plot all levels corresponding to n static. So I have like discrete parabola. The spacing between the levels within a series increases. But well, I have to plot all series together. And if I bring all these energies together, I don't see much order already. There are some discrete, there's some rather chaotic system of levels. We will see that it's not quite sure. We will see the difference between this geometry and typical chaotic geometry. But let us discuss it later. Anyhow, we have discrete levels. We know how to deal with that. Good. We want to do something, and change some experimental parameters to affect quantum dots. And one of the easy parameter would be to apply a magnetic field perpendicular to this dot to affect electron motion inside. Well, the point is that for square dots, the levels which are so easy to find without magnetic field are difficult to find in magnetic field. So to understand the effects of magnetic field, let me look at even simpler model. Or perhaps not simpler, but yeah, equivalently simple. Right. So what would I assume now? That the dots made in the same two-dimensional structure is make somehow a ring. So electrons can propagate within this white area in ring shape form, and their motion is quantized in the direction, in radial direction, right? So I could just disregard it and consider one-dimensional quantum dots. Good. Sorry, one-dimensional motion along the circumference of the ring. Fine. What do I write for this? Just kinetic energy. But I also want to bring into consideration magnetic field. So I will do as usual at the Hamiltonian level. You elongate momentum with vector potential of electromagnetic field. Good. Magnetic field is in the direction perpendicular to the plane. Right. And vector potential, we remember, just winds around electron magnetic field. So vector potential in this case will be in radial direction corresponding to the direction of momentum. Fine. So what is good to do now? Just introduce convenient coordinate, which is actually the angle. Let me draw it. That's going to be coordinate phase phi. All right. So one would rewrite momentum in terms of phi, so derivative will be with respect to phi. And if one takes into account, if that substitutes the radius of the ring, after the substitution, vector potential would be total flux, so the whole ring, like in Aronoff-Bohm effect, divided by flux quantum. Fine. So I just write this equation of convenient coordinates. And what is Solution to this equation. Solution to this equation are also very simple. It's a plane wave. It is a plane wave, right? Corresponding to quantization of a wave vector along the ring. Periodic boundary conditions, so we don't have waves propagating in opposite direction. They always go either clockwise or counterclockwise. All right, so we have discrete number labeling these solutions. And well, we substituted to the Hamiltonian and we get energies of the levels which are now affected by magnetic field, by the flux through the ring. If I plot it versus flux, I obtained the picture which we have already seen in the context of Coulomb blockade, the picture of shifted parabolas. So for any given n, we have a parabolic dependence on flux. But since there are many parabolas, one has to sort energy levels. So all of the most pieces of parabolas is eventually ground state, then the first excited state, then the second excited state. In this way. Fine. Let us see. This discrete number n. Who can guess how one would call it differently? How you called it in your first course of quantum mechanics? I'm sure you did. Perhaps you don't remember, well, but it's somehow a question about something which you know or should have known. All right. Yeah. Yes, Jan Brian. It is precisely angular momentum. When talking about wave functions in air terms, we consider the states of with full momentum and also with a certain projection of momentum into a given axis. So there was, for instance, some function which depended on two angles, and the dependence on the angle perpendicular to the axis was expressed in pretty same way. The only point they use letter M for this convenient notation, and it is called, this is projection of quantized angular momentum onto that axis. In our case, this is axis perpendicular to the plane we are in. And okay, this is also called azimuthal quantum number. Fine. So we have classification of the states in terms of angular momentum. And for each angular momentum, there is a certain magnetic field dependence. And changing magnetic field, we eventually make the states with different angular momentum energetically favorable. That's nature. Magnetic field wants to bind electrons. And right, the more magnetic field you apply, the more angular momentum you got. Fine. Let us look at it from a little bit different perspective. Let us, following scientists of the past, let's find a fancy name for this. Of course, the dot is isolated and there are no currents in this system, currents to be measured electrically. But in fact, the magnetic field, as we have seen, give rise to angular momentum. So it changes electron motion, it magnetizes electrons, and they, in its own turn, also produce some magnetic field. There is an electron current which is associated with this angular momentum motion, winding of electron trajectories, and it is called persistent current. Again, it's not real current which one can measure in electric circuits, but one can see it as a magnetization current, response of the dot on the magnetic field. Well, how to derive it? If one knows the energy of the dot, its derivative with respect to flux is precisely this current. This type of relation we have already seen in Josephson effect. There we differentiate with respect to Josephson phase. Now it's flux, but the effect remains the same. There's some current, which is the property of the ground state. And is expressed through ground state energy. So how we now compute this, how we assess this persistent current? Well, we just sum over all field levels in the box. And differentiate it over flux. It is interesting to note, and perhaps it's good to come back to this picture to show it explicitly. Let us fix a certain value of the flux, and let us look at the derivatives. All right, we sum up the derivatives with respect to flux, and we see that this derivative is negative, then there's positive, then there's negative again. So the derivatives tend to alter, right? Which means that the whole effect wants to be cancelled in the limit of big number of levels, and main contribution just comes from the one level from the last lecture. All right. Yeah, I guess I plot this current for several, just for the model I considered, which is a rather crazy model. There is no scatter in the dot. That's why the result's a bit fancy. And red, blue, green lines correspond to 1 electron, 2 electrons, 3 electrons. You see the current jumps, and who can for each type of curve. So who can tell me why? I believe it's easy to see this picture. Yeah, avoided crossings and other angular momentum becoming more favorable. Oh, right. Okay, so one could just concentrate on the ground state and its derivative And we see that the derivative jumps, right, because there is switching to another value of angular momentum when we change magnetic field. That's why there are jumps in the current. If there is some scattering, suppose there's some impurity in the dot, then it will give rise to a mixing of different waves. And as such, the degeneracy here will become avoided. I'll exaggerate a bit. Good. And in this case, kind of current also becomes continuous, but it changes quickly near the level crossing. Good. This is about persistent currents. People kind of measure it, although it seems to be a difficult experiment. Well, basically, they were airplane. They make several dots. They apply magnetic field. They measure magnetization. All right, it's very tiny response. But perhaps somebody get an idea how do they focus on the response of the dots as compared with the magnetic response of substrate of everything which is around in this experiment. The hint is in this transparency, of course. Good. It's all periodic in flux. Yeah. So they concentrate on they make the dots of more or less the same size. And right, they look at the part of magnetization which exhibits oscillatory dependence. Fine. I'm a bit out of time, strange. And let me just go faster. Good. So that's all about the levels. Let's have some states. All right, it is easy. So let's take the dot and let's take a certain number of electrons, given number of electrons. And let's place these electrons to the dot. They all go to the lowest levels and they will occupy these levels. All right. So this is a ground state. So all these green levels are occupied, all purple levels are free. So that's first state. Now let us arrange another state. Let's make the lowest excited state, first excited state. I don't talk about spin yet. I can arrange that. Well, I could just take an electron and put it here. So there will be extra electron in empty level and a hole in a field level. Good, that's one of the possibilities one can make. Other possibilities. And then we kind of encounter a law of multiplied possibilities. Let me talk more about this. Let me talk more about possible states in a quantum dot. Right. For simplicity, we assume no interaction, and we, in this case, we can classify all states by number of electrons excited. There must be the same number of electrons and holes, since we don't change the total charge of the dot. So there will be states of phase generation, right, corresponding to different placings of electrons and hole. There will be states of second generation, and so on. Right. For any state, the energy would be just sum of excited electrons minus sum of excited uh, levels. Okay, I've got a formula, but let me first just illustrate it with an example. I've taken this system of levels, so there are energies of empty levels, energy of the field levels, and they're quite spaced, right? In general, for energy strip of energy E, well, to get the number of levels, we just divide it by average level spacing. Okay, and what did I do here? I plot the energies of the states of first generation in black, second generation in red, third generation it comes blue. As you understand, okay, you pay more energy to excite more electrons, so all the spectra they start with increasing energy. But it's what is more important for me. It's a level spacing between these states decreases quite fast with increasing energy. So I have kind of about a dozen of levels over here, and here I have about 1,000 of states. Indeed, one can make a correct estimation for this. The number of states in energy strip of E is in fact exponentially big. What you find in this exponent is square root of number of levels. Right. So because of many combinations, the number of states in quantum dots will increase pretty fast with energy. That makes an interesting addition to our definition of quantum dot. Remember, we define quantum dots as something where states are visible, right? But you see the number of states increases with energy. More and more states can be excited. So, in fact, quantum dot will cease to be quantum dot at rather at high, but rather moderately high energy. That's it. That was interaction. Let me tell you several words about the significance of interaction. Perhaps one of the most interesting effects of interaction, which is also widely used in all in devices related to quantum dot, is that interaction splits and sort states with respect to full spin, so-called exchange interaction. Let me recall the first excited state. We have agonized, exciting one electron and leaving a hole behind. In fact, both electrons and holes can come with different spins. So in fact, we have 4 states. These 4 states can be arranged according to laws of spin in a singlet state, which is kind of linear combination of these two, and 3 states of triplet with full spin of 1. So the component with spin -1 is this one with spin plus one, this one. And the third component is again a linear superposition on these two. Good. And these states are have different energy as a result of interaction. Good. Also, it kind of mixes the states of different generations. So, in fact, the states become superpositions of the states of different generations, but it's not that interesting, just doesn't show up as a big effect. Right. The most important effect of interaction in quantum dot is something which we already know. We have studied it in lecture number 5, namely its charging energy. So let me talk quickly before the break about charging energy in quantum dots. Let me imagine the same situation which we had in Coulomb blockade. So there was a metal electrode to supply it electrons. There was a gate to tune the number of electrons, but instead of metallic island, we've got a quantum dot. Same stuff. This charging energy to pay. This charging energy proportional to number of electrons minus some number of electrons squared minus some addition, some discrete charge due to the gate, where in the gate potential one can make the states with different charge energetically favorable. Here, I guess this line is hardly visible. I plot here a number of charges with respect to the gate. What was the difference with metallic island? Metallic island cannot be emptied. One could not extract all electrons from metallic island. One could do this for the dot. So here just means that at certain gate voltage, the dot is empty. What can be mentioned? Level spacing is much larger in the dot than in metal, but Coulomb energy still a little bit, at least by a factor bigger than the level spacing for any type of the dot known. This capacitance, well, in fact, it slightly depends on number of charges, or one could put charge and energy, which is also slightly depend on n, but in concrete experiments, they usually can neglect it. Right, that's it, charge and energy. Now we have everything to start talking about transport in quantum dot. And let me do it after, well, perhaps 5-minute break. So we start at 9:14. Very good, ladies and gentlemen. Let us go on with the lecture. So we have understood there is a strong charging energy in quantum dot, which means if we want to arrange the transport, the quantum dot, we necessarily encounter Coulomb blockade. So let me first discuss single electron transport in a bit general terms and look at the difference between single electron transport in metallic island and in the dot. The complication of quantum dot that the states in the dot are real quantum mechanical states. in distinction from metal island, where the state disregarded all possible excitations within the dot, just was a state given by a single number n. Here the states are given by n and something else. There are many states which differ by s, and correspondingly they have different probabilities. Okay, what are the transitions? What are the rates which affect the transport? Good, we have single electron rates pretty much the same as in our earlier consideration of Coulomb blockade. So electrons come one by one. Well, they have to go to some other states, or in quantum dot, it also depends on the transitions between different pairs of states. In addition, we have also relaxation. There can be transitions in the dot, not without electron change. Here, for instance, excited state, which we have discussed, could go to the ground state, and electron could go down, emitting a photon, something like that. Good, suppose we know the rates, then the problem of electron transport is easy. We just write down master equation as we did for Coulomb Island, solve it, it gives us all currents. Let me talk about single electron tunneling rates first. We have the same energy consideration and yes, in Coulomb blockade. It is important to understand the difference of energies between final and initial state. And this energy must be negative. Since everything rolls down and nothing rolls up, right? So it is just energy dissipation. Right, so if the temperature only the rates with negative energy are negative energy change are allowed. And it is also good to know that in distinguish from big islands, the rates in quantum dots hardly depend on energy if energy difference is negative, if they're allowed. Right, so just for make sense simpler, we can talk about the rate which describes the tunneling. From say from to a given level through a contact. Let us find the relation between these tunneling rates and the conductance of the contact between the dots. I believe that we did it in the last lecture, but I can anyway, let me repeat it again. It's a simple calculation. So let us imagine some system of levels in the dot, and in average, these rates are separated by level space in delta. Let me now compute the total current. Suppose I've emptied n levels over here, and I wait for transitions of electrons to the emptied levels. then the total current will be proportional to the number of empty levels, and that will be given by number of the levels in energy strip of the order of voltage. So we got current proportional to voltage, but proportionality coefficient is eventually conductance. So that relates the decay rate gamma to the conductance of the dot. Right. That also, by the way, proves something which I believe I gave you without proof, right? Namely, that for discrete levels, the conductance must be smaller than conductance quantum. Indeed, in this case, well, what we do compare, this ratio is in fact the sum energy uncertainty of the level, which is gamma. And I compare it to typical energy difference, which is delta, right? And if the spread of the level is bigger than the difference between the levels, I cannot already tell that these levels are discrete. Good, so that's where this requirement comes from. Good, we have estimation for single electron tunneling rates. As to relaxation, yeah, they can come from variety of mechanisms, and it doesn't make sense to talk about them in detail, since these details do depend on how do you make the dot, under which conditions you hold it. Let me just tell something about these relaxation rates, keeping generality. In any case, this relaxation, yeah, it is related to some energy dissipation. This dissipation can occur by emission of phonons or photons to some excitations which go away from quantum dots. That's natural, and it doesn't involve any channeling from the dot to the lid. Just to unleash our imagination, this excitation can be also an electron excitation in the leads, not involving any tunneling. Here I got it. So there was excited electron hole pair in the dot, and there is a lead nearby. And although the particles do not tunnel, they can kind of emit a photon, which is absorbed right away in the lead. In this sense, after absorption, there will be electron hole pair created in the lead. So there's also an interesting, strange process which can determine relaxation. Good, relaxation rates. And let me now look at a very simple but very interesting particular case of transport through the dot, which is, for some fancy reasoning, is called resonance tunneling. There is no obvious resonance in this consideration. What we want to have is a transport at very small energy differences, smaller than the spacing between levels in the dots, right? Then we can arrange the position of energy levels in such a way that only one electron is in a window of chemical potentials. Okay, there's a difference between field electrons on the left and field electrons on the right. Only a single level is between these two, is in this energy difference, right? In this case, the dot can only jump between two states, namely ground state with n and n plus 1 electrons. Fine. How do we see this in a plane of gate voltage and bias voltage? Suppose bias voltage is 0, then basically we don't have any current unless the position of the level, which is affected by gate voltage, precisely coincides with Fermi level. Here it is. Then we increase bias voltage, and we see that transport current persists in this area, which is in fact a part of the Coulomb diamond, right? So there are a part separating two Coulomb diamonds at n electrons and n plus 1 electrons. Right, so in this region there's a current. To estimate the current, one just needs to know the rates of coming from the left, going from to the right. Those rates hardly depend on energies, and the current, one can prove it from master equation, for instance, is given by this expression. Here I did not talk about spin, kind of let us say for simplicity that there is no spin degeneracy and there is only single state coming into the play. Fine. This is resonant tunneling. Interesting question is as follows. Since gammas do not depend on energy, the current is just constant within this allowed region and is zero otherwise at zero temperature. So there is a sharp step of the current which formally gives rise to infinite differential conductance. Yeah, you differentiate jump, you get infinity to the point. So the interesting question is what smoothes this sharp step in the current? Well, it can be done by temperature. And if this temperature is bigger than the decay rate, indeed it does. So instead of sharp edge, we have some spread at energy distance given by temperature. I don't write KBT, KB. Right, so that gives rise to a conductance, which, as you see, now just current divided by this, is inversely proportional to temperature and somehow wants to diverge at low temperature. Yeah, of course, that is false divergence. It should not diverge. And in order to estimate it, we understand that this doesn't work if the temperature becomes smaller than the level width, right? So the levels are in fact not sharp, the spread at the energy scale of gamma, right? So we have the current proportional to gamma, the width proportional to gamma, and we have estimation, which is just conductance quantum. Well, irrespective of initial conductance, conductance of the dots of the contact can be very small. But here, at this particular point, we've got conductance quantum. Let us now recall lecture number 2 or lecture number 3, doesn't matter. We've been talking about transmission resonances internally, right? We've been talking about two-tunnel junctions, and we have discovered that sometimes there's almost ideal transmissions of these junctions. Yeah? It's also kind of another manifestation of the same phenomenon, but now in quantum dots. And anyway, it involves one discrete level, one resonance. Good. Also, if you take spin into account, all this is modified, but only quantitatively. There's still the same estimation for conductance at the step. Fine. Let me just say quickly, and there's kind of related homework, and again, there's a chance that it will appear in exam as something to something to do during the exam. It's a picture of a transport at a little bit higher energy. Right, so what did I do to draw this picture? Well, I'm still consider two different numbers of electrons. Say this is n, and this is n plus 1. But now I allow for two states in each for each number of electrons. So previously I considered only ground states. Now I add excited state for each number of electrons. Well, I have already quite a sophisticated picture of the transport. How come? Well, what I plot here is our zero energy differences between all pairs of states, right? And they define different regimes of transport with different currents within each region. Right, so for instance, here we find only state A, here only state B. Here states A and B can come together. Here, for instance, 5, state B prime, first excited state for n plus 1 electrons come into play. You increase the voltage, more and more states are involved. What is important for me at the moment are these lines separating different currents and correspondingly giving rise to enhanced conductance, right? So these lines can be seen in IV curves of the dots, and they eventually give the positions of excited states, the positions of the levels. All right, so let me show you a kind of experimental picture. And we will look at diamonds and experimental quantum dot. This quantum dot is eventually made in a carbon nanotube, which used to be popular. At some stage, they're flexible with respect to position. It's not metallic, it's made of carbon. So what one can see here, first diamonds, no current. And the intensity of black is differential conductance. So, okay, that's the reliance one can see. I have shown it in the previous picture. In this way, one can see in the plot the energies of first excited states. For each number of electrons, there are different excitation, different excited states. Also, if you increase voltage, you see more and more states coming into play. So at a rather big bias voltage, it all becomes a mess, and the spectrum is continuous like for metallic island. Good. That's what I wanted to say about the transport. How I'm doing in time. Oh, that's not bad. So let me move to random matrices. So we have yet another change of topic. We understood levels, we understood states, we understood transports, we understood that transport measurement gives energies of excited states or for the levels. Let us talk a little bit more about single level energies in the dots. And I will start with perhaps a bit strange topic. I will talk about classical mechanics, and I will outline the difference between regular and chaotic motion in classical mechanics. So let me think of box potential as we applied for the dots. Let me let me look at electrons which fly in this box potential. Again, let's talk about two dimensions. Otherwise, I don't want to draw three-dimensional pictures. Good. Square geometry. Any trajectory is ultimately simple and just repeats itself. So classical electron just reflects from the sizes of the box. So there's very regular self-repeating trajectory anytime. Good. And this is why we could easily crack quantum problem, because it's also the same as to say as a motion is separable in both dimensions. So let me look at the how do you call it, cylindrical symmetric geometry. Let me talk as a trajectory in a circle. It's not a ring, it's a circle. I draw a trajectory. Okay, it looks a bit complex, but it is still regular, right? So what I draw here, let me do it in time domain. The angular momentum conservation, so electron with certain angular momentum cannot get closer to the center. So it goes like this with many reflections. So trajectory is more complex than this, but still it's pretty regular. Well, it's also because one can separate motion into two parts, radial motion and angular motion. Yeah, but if one just changes a little bit the shape of this confining potential, the situation with trajectories becomes completely different. And the people, especially mathematicians, were quite excited about this at some point, right? They discuss classical mechanics and trajectories in what they call billiards, whatever has very little to do with snooker, but it's something which has such shape, which differs from a circle shape just by inserting, funny enough, a rectangular section. All right, so it looks like a slight modification, but the picture of classical, again, we are talking about classical motion becomes completely different. In fact, trajectories in a billiard are not regular. They don't repeat themselves. And in fact, each trajectory explores the whole phase space. At a given energy, it goes through all possible values of momentum and coordinate, which correspond to this energy. Sooner or later, any trajectory will pass a given point with a given momentum if it's allowed by conservation. This is called chaos. Yeah, and already from the definition of this ordering chaos, one sees that something is perhaps there is something subjective with our understanding of order and chaos. One could imagine a point of view in which the chaotic motion, in fact, is more moderate. Well, it just fills the whole phase space. It's simple. While trajectories we are called ordered, we called ordered, they can be also rather complex. So perhaps it's a little bit subjective and just a changing our viewpoint. You can see order in chaos, and chaos in order, whatever. But this is kind of common point. I wonder about the following, like yet 10 years ago, this topic was very popular among the students. Many students somehow got, I don't know, from popular literature, some notion about chaos, about chaotic trajectories. How about you? Who of you knew the facts which I just outlined from some other source? All right, I guess it's a topic in general interest. Many physical systems correspond chaotic behavior. Well, I even read a book about financial markets, which actually made the point that markets are described by chaotic equations. So it's an interesting topic in general. Fine. Okay, but we're still talking about classical mechanics. Let's understand what's the manifestation of chaos in quantum mechanics. Right. And in this respect, we come again to this two gentlemen, which we have shortly mentioned in previous lecture, Wigner and Dyson. And they made a big conjecture. They drew a correct association between random matrices and quantization of chaotic systems. Right. So let me first talk about system of levels, some complex system of levels in a separable geometry. An example of this is a box we have discussed, square box we have discussed in the beginning of the lecture. Or it could be, for instance, hydrogen atom. Hydrogen atom without magnetic field is an example of separable geometry. That's why one could compute all these levels in the atom. Right. So we see the levels. They don't seem to be very ordered, but you see sometimes they come very close to each other, and that means that they belong to different series which do not talk to each other, which do not notice each other. That's a typical spectrum of separable system. Surprisingly enough, it doesn't come very far from opposite extreme. And this is a spectrum where levels do not talk to each other absolutely. They belong to different systems. And in this case, they just independent states, they assume Poisson statistics. And indeed, also in this case, we see small level spacings and large level spacings, all completely random. But if one takes chaotic system, the point, the slogan behind this, that in chaotic system, there's repulsion of quantized levels. And owing to this repulsion, levels become a way more ordered than in both cases of separable geometry or in Poisson statistics. Yes, that's a pretty intuitive picture. We put some particles subject to fluctuations. We can find them. They repel each other. So they like to be at, they like to avoid extremes, very small and very big separations between distances between them. So it is Wigner-Dyson statistics. Right. Oh, sorry, I went back. And with this, we talk again about random matrices. Let me, for this case, tell a little bit more mass about matrices, what's eventually this statistics. So, what are models used in random matrices? Right. So, you take a matrix, n by n matrix with a big N because many well levels are involved. And we assume that all this matrix elements are zero average. But yeah, there are some fluctuations of this matrix element at the same position. This is correlation of two matrix elements. This is distribution, which is assumed to be normal distribution, Gaussian distribution. Fine. Let me say something simple about the origin of this level repulsion, which kind of seem to come out of the blue. I just told you that levels repel each other, and you kind of believed me. Well, there are all reasons to believe me, but let's get some intuition for this. And to this end, let me just consider very simple matrices. Let us just consider 2 by 2 matrices. And we will be talking about two types of these matrices. All right, first, unitary ensemble. Well, in this case, it's just an arbitrary Hermitian matrix. So as such, it has 4 independent components, 3 components corresponding to Pauli matrices Z, X, Y. This component, which is the same, is not relevant because it only shifts both levels. It does not change level splitting. All right, so what's the level splitting? Okay. It just sum of the squares of these 3 components. Square root of this, so it's a vector distance in 3 dimensions. Both all these components are independently distributed and independently fluctuate. And now if we want to assess the probability to have certain distance, how do we do this? Well, we have integration over all 3 components. All right. And now we need to concentrate on radial direction. A radius is this, so it can be like in common geometry, can be rewritten as s squared ds, which means that probability vanishes. This is the level repulsion. So it just comes from this transformation of integration element. Alternative which we can consider is so-called orthogonal ensemble, and this is one of real matrices. Real matrices which are typical for systems which respect time reversibility, which is time reversible. What is the difference? Y component goes out of the play. So we have only 2 independent components for this matrix. Therefore, we integrate in 2 dimensions. Y component which disappear. And there is only first power of S. Good. So we get a little bit slower repulsion proportional to the first power of S. That's a kind of simple explanation of this mathematical fact, of the mathematical fact behind level repulsion. We just could understand it for 2 by 2 matrices. Question from Sasha: could you repeat how you calculated S from the matrices? Right. What is asked first? S first. S is a level spacing. So I took this matrix, I diagonalized it, I got 2 levels, and those are separated by twice this quantity, right? So it just finding eigenvalues of this matrix for 2 by 2 matrices. It's pretty straightforward. Right. And then I rewrite the probability distribution of these matrices in terms of this level spacing. And since level spacing corresponds to distance in either 2 or 3 dimensions, it gives rise to level repulsion. Fine. Oh, eventually now I kind of steer ahead of schedule. Good. Anyway, there's not so much left to say. So there's repulsion. Now we got it for conjecture of the Wigner-Dyson, which is generalization of these to many levels to large matrices. So there's repulsion between each pair of levels, right, with a coefficient, which, as we have computed, is 1 for orthogonal ensemble, 2 for unitary ensemble. And there's yet another ensemble, we have mentioned it shortly, there's yet another ensemble of symplectic matrices, which illustrate the case of systems with strong spin-orbit interaction. Good, there's repulsion, there's potential which confines the levels, and you see the spread of the levels comes in the definition of this confining potential. Fine, Wigner-Dyson distribution. One can see this Wigner-Dyson distribution in the levels in quantum dots. And originally, as I told you, that was from Wigner-Dyson began to think of this distribution when they studied experimental data in nuclear physics, where the properties of different nuclei were so various that, yeah, that they in fact have been stochastic. Fine. So we talk about random matrices. Let me mention electrostatic analogy. This probability distribution can be regarded as a statistical weight in a certain potential. Boltzmann distribution and temperature corresponds to the ensemble. Right. This logarithmic repulsion can be arranged if the charges are eventually in a line perpendicular to the plane of the slide. Right. In this case, electrostatic repulsion is logarithmic. Good. If temperature is 0, which is not the case of random matrices, these matrices are not random, but for this model, zero temperature would imply that there's a regular lattice of the levels, which means that the levels kind of do not fluctuate. Right, let me talk again about spectral rigidity, and I have a small bonus story to illustrate this example. Right, we have shortly mentioned it in the previous lecture. Good. Let us consider levels in this random chaotic system in energy strip E, and if spacing between levels is delta, we have that many levels in average. What's the variance of the number of levels? And if kind of levels are independent, the levels are kind of independent, completely individual. All right, the variance is estimated by Poisson distribution. Variance is proportional to n. We remember there's a link to measurement, which is repeated n times. And that means that the accuracy, which is given by variance, is 1 over square root of n. Right, that's something which you should have remembered from your, at least I learned it during my first physical practicum. Fine. So there is rather large variance of number of levels if the levels do not know about each other, do not talk to each other. So what do we have for chaotic system for ensembles which obey Wigner-Dyson distribution? If we take a kind of sharp strip with different with sharp edges, number of the variance of number of the levels, just first of all, average number of the levels will be precisely the same. But variance changes drastically. It depends on the order on this inverse temperature. It's different for different ensembles, but it is kind of case of like logarithm. And in fact, all logarithms are of the order of 1. So the variance are in level ensembles which are chaotic. Remains always of the order of 1, irrespective of the width of the strip. So here it grows very fast with increasing width. Here it does not change. And this property is called spectral rigidity. What does it manifest? The levels are not independent. The levels come from the same random matrix. That's why they correlate. All right, bonus story. Let's talk about our society, and let us forget about pandemic conditions. Let's talk about our society as we remember it. This is city of Delft with 10 to the 5 inhabitants. All right, again, I assume normal situation. People come and go. They go to different cities. They go to for jobs. So what could be a variance of number of inhabitants in this city? Well, let's take square root of this number. So we get like 10 to the 3 to the 10 to the 5 square root. Fine. That does not seem crazy to us. Yeah. So there are all these fluctuations. People go to different cities. People go to job. People looks like reasonable number. Fluctuation of momentary population of the city. All right. Let us have as requirement that variation of the number of inhabitants at all cases is of the order of 1. Good. How one can arrange it? Yeah, perhaps you can give me a better recipe. As I see it, one has to build a wall around the city, put barbed wire along this, and just leave a single gate, a single checkpoint to check whatever papers, to check the right of a given person to exit or enter the city. So that assumes very different society um, from very different from which we get used to. Society where all members are kinds of rather dependent on each other, rather collectivistic society. Good, that was the bonus story. Sir, I finished my presentation and I remain for a while to answer your questions. Let me stop the video.